this is Steven. Today what we're going to do is look at a continuation of a previous topic, which is, can we possibly do a 4.7 megaohm pull-down resistor? Typical values you see in the field, 10K, 100K. I think I've seen 324K once. So if we can somehow pull this off and get a 4.7 megaohm pull-down resistor to work, this is significant power savings in your project, because you don't usually have just one of these in a circuit. You have many pull-down resistors. So this can add up and give you significant power savings in your project if we can prove that it works. Now, in order to do that, we got to have a board. And the first thing is a schematic. So we're going to go through this schematic right here. So what you're looking at here is the actual circuit with the pull-down resistor. We have, what I did is 12 volts coming in. Then we've got a total of 12 ohms right here. So this is a bunch of power resistors. So 3.5 watts each, that's more than enough to handle that. I didn't know if I really needed to put a load on here or not, so I just said, When you see the rest of the circuit, you'll be like, oh, you just duplicated it. So I didn't know if there'd be any kind of leakage between drain and gate or not. It doesn't look like it, maybe minimal. But with 4.7 meg, minimal might be too much. So we're going to see. So this will take on your DC. Any AC components, this capacitor here will take care of. I've got termination resistors on both ends. And should this thing turn on, we'll have an LED here. Another reason for the load is because on my power supply, it'll show up. So I've got two different ways of seeing this without scoping it or anything like that. Another thing to mention, I can't really use an ordinary scope on this line because of this huge impedance right here. I would need to go to work, get the $10,000 scope with a high impedance probe. And that's just not going to happen. So we're going to just rely on good old-fashioned techniques here. So let's go through the rest of the circuit. So we're going to zoom out. We're going to start where power comes in. So we're going to have 12 volts running on the circuit, hence a 12-volt TVS diode. So I don't want to ESD my board to oblivion. So another thing we have is just a regular ceramic cap next to this. It does two things. If there's any high frequency components from the power supply, this will get that out of there. Also, this serves as kind of a secondary ESD protection. Some of my stuff in the circuit is can't take too much more than 12, so this is good. So I'm going to have a total of probably like 3.1-ish, 3.2 amps on this circuit. So what we're going to do, kitty. So what we're going to do here is have these bolt caps up here. And we'll be able to handle that. On the right here, just a regular linear regulator. 12 volts on the left. Then we go 5. So that goes below here. So I just chose a AT Tiny 13A. It's cheap. It's plentiful. It's easy to work with. Data sheet's great. I don't need all that many features. So, yeah, man. What more could you want? Cheap, simple, easy. Unusual things. I did these 200Ks in parallel. Data sheet for the, well, no, it's not a data sheet. It's the user manual for the programmer I'm going to be doing. So I've got this here. Pick kit 4 is what I'll be using, unless I have a 5 somewhere. Don't know if I do or not. We'll find out. But anyways, it said for the pull-up, 50K at most. So 10 to 50 is what it said. That's fine. Shout out goes to bypass cap. Everybody uses 0.1, but I made another video about this. Bigger is better. So I'm using datasheet for this said, hey, all of our testing was done with 10 microfarads. So I was like, all right, well, I'm gonna use the 10 and I'm just gonna stick 10s everywhere where I need a cap. There's no harm in doing this. Also, it helps me that way I don't have to get 1s and 0.1s or whatever else and deal with that. Because I'm gonna be hand soldering this. So I don't wanna get a whole ton of unique components. So this is just better. Then we've got, let's go to the fun stuff. Okay, so our signal with the 4.7 mega ohm is going to be going right through the middle here, next to this 12 volt 1 amp trace, next to this 12 volt 1 amp. Directly next, as close as we can get, because what we're going to do is try to create as much noise as possible to make this thing fail. Now, in order to do that, since we're intentionally trying to create noise, there's 3 ingredients. You want a high voltage, which we have 12 volts. We want high current, 1 amp. And then we also want high frequency. So this thing's internal oscillator is capable of 9.6 megahertz. So you have I'm going to be doing a 50% duty cycle. So we're going to be doing 4.8. So we got all the ingredients for an EMI nightmare to try to get this thing to fail. And if it works with this, it'll probably work on most circuits out there. So let's zoom in on one of these. So we have our signal here, high frequency. So this is really the first project I've done where I've had my programming pins and my legitimate signal pins together, because I have a low pin count here. I don't normally do this. What I normally do is just spec something with a shitload of pins. That way I have dedicated programming pins. But I don't have that luxury this time, so this will be somewhat of a learning experience. So this is why on that signal I put a 0 ohm resistor there. That way, in case having this here, this EMI nightmare causes issues, I can just flip this component off, program it, put it back on, end of story. A 1K pull down resistor is a little bit unusual, but because my signal is fast, I need a strong pull down. Keep that as square as possible. Now, this thing right here, the microchip NCP1416 gate driver. So I don't think a gate driver is strictly necessary for this project, just because these GPIO pins can do significant current for what we're doing. Maybe. But I got a gate driver anyways, just because I need square waves. The more square, the better, because I want that EMI. And then this thing needs a bypass capacitor. So, oh, yes. In a real project, you always want some kind of notes. Like, because what I'm not putting on every component is, what's your tolerance? What's your wattage? I guess I did for a lot of these, but if it's your typical 50 volt capacitor, I don't want to put that 1,000 times. So it's just, if you put those notes there, that means you can put less for on all these components to make it a little bit cleaner, a little bit easier to do. Another thing I did not do is like put blocks around here and say, this is the power. Here's our voltage regulator. Here's our microcontroller. If this was like a very professional project, yeah, probably would have put them in. But for something relatively small like this, it doesn't bother me because I do things in a way where it should be easy to eyeball. That's where I'm going with this. I want my circuits boring and eyeballable, if that's a word. Because boring means, well, one, you can eyeball it. Two, your components are going to be easy to source. Three, anybody's going to be able to not have to dig and dig and dig and dig through piles of documentation or data sheets and whatever. They know what you're doing. So with that said, short video today, easy schematic. Next video, what we're going to do is the layout for this. Now the layout is anything but simple. The schematic just shows us how things are hooked up. This is simple, but the way we had to actually do the layout in order to do all this noise and to sufficiently test this was something else. And it was a good one. I had to do things I never thought I'd do in a circuit. So hope you look forward to that video. I hope you had a good time on this one. Feel free to leave questions. I will respond, promise. Thank you.